Okay, so we press a physics book against a wall hard enough to keep it from moving. We're supposed to draw a free body diagram for the book. First thing you might do, because it's often the first thing you do when you solve a problem, is you might try drawing a picture. It doesn't need to be a very good picture. Okay, there's my hand. And as we draw the free body diagram, we always start with a dot. An obvious force acting on it is the weight of the book, which I could write as mg. The friction is going to point upward. And what type of friction is it? Static friction. And I noticed a lot of people had a hard time figuring out which way the friction was pointing as I was walking around. So in the middle of a test, if you don't know which way the friction is pointing, grab a book and go lean against a wall and see if you can figure it out. That's okay. Just don't disrupt anyone. Oh, totally. Just as long as you're not being disruptive, that's okay. And truly, with any physics question like this, what should you do if you can? Yeah, try it. I mean, that's what physics is all about. The wall is pushing against the book, and that type of force is a normal force. And I might say the normal of the wall on the book, because the hand is also pushing against the book. And truly, that's a normal force too. I guess you could say the force of the hand, but probably the normal of the hand on the book would be slightly more appropriate. And, you know, in my picture, maybe the hand was pushing up at an angle, so if you had an angled in there, that would be okay. But regardless, what is the F net in this case? 0. Okay, let's try. Yeah.
So the static friction, there's no normal force in that?
Okay, so the question was the static friction. We could write either F of S for static friction, or as we've been doing in class, we've been instantly turning that into a mu S n. Whatever you do, don't write just mu S, because mu S is the coefficient, and it's not a force, it's just a number. Thanks for asking.
Would it be okay if you wrote the NH on B as FH, that is of H on B?
Yeah, you know, if you did F of H on B too, as long as a reasonable person could understand what you were saying, it's okay. Okay, number 6. The car in this picture is rolling down the hill at a constant speed. Let's draw a free body diagram for the car. Of course, all free body diagrams have a net force. We always start with a dot for our car. It has a weight. The weight is going down towards the center of the earth. The normal force is pointing perpendicular to the surface of the plane upon which it's going down. And then we have a tension going up, and the car is rolling downhill. So we do have, we got some friction here. What type of friction? Rolling. It's not sliding down, but it's rolling down. So probably that should be a mu Rn there. And you always need an F net. Which way is F net pointing in this case? Constant speed. So that means that F net is equal to 0. And if we were being 100% correct about it, we should make sure that we put in axes. Again, because you're not solving the problem, it doesn't really care. It doesn't really matter if you use parallel and perpendicular axes or if you use a more X and Y type. But the F net has to add up to 0. Okay, number 7. We're given the solution to the problem up above, that the acceleration is equal to this equation, and we're going to use at least one limiting condition to test whether or not the solution makes sense. So as I was wandering around, a few people tried something like theta car equals, okay, an extreme might be 90 degrees. And if we chose that extreme, we should then draw a picture. And this would be the picture. And if I were to look at the equation, I know that sine of 90 is 1. So this would give us an A net equals m car subtract m weight sine theta weight over the total mass all times g. Is that a nice simple equation that screams, yes, that makes sense? No, it doesn't to me. So maybe you should try a different limiting case.
We try taking out another, change another variable in there to take the counterweight as 0.
Okay, what we could try doing is we could try, yeah, we could always do that. We tried one limiting case. It didn't really help us much. Let's then, let's just try doing a different one. We could try editing that one more, but let's look at a different one altogether. We could try something where maybe we've cut the rope for the counterweight. And if we cut that, that's equivalent to saying that the mass of the counterweight is equal to 0. You know, it's not very useful when counterweight and car both start with C. And in this case, that's now just a car rolling down a plane, and equation-wise, that's going to give us that A net is going to equal m car sine theta car. All the rest is going to go away, except for the g, and that's going to give us that an A net equals g sine theta. And has we seen that one before? Yeah, way back many chapters ago, whenever anything was sliding down a plane, the acceleration was g sine theta. So that would be at least one test that gave us a nice, quick solution. We could, as you suggested, try that test on our previous approximation, and it would give us a reasonable result as well. What's another one you could do that would be?
Theta equals 0.
We could do a theta equals 0. And I think that's going to give us, again, a non-obvious answer, maybe because you did a homework problem like that, but maybe not. There's another one that's really, you know what the answer would be. What if we made the two thetas the same and the two masses the same? What would we expect happens? Nothing. It should just be in static equilibrium. And if you want to, you can sit down and play with it and see if it works. Actually, you can kind of look at the top part, and you can see the top part does just go to 0 if you do that. Okay.